In this video, we shall look at RL circuits. R stands for resistor with resistance R. L stands for inductor with inductance L. In an RL circuit, the resistor and the inductor will be connected in series with each other, as shown in this figure. So the one in blue is the resistor with resistance R, and the one in green is the inductor with inductance L. This is the battery with an EMF E. The positive terminal of the battery is that, and negative terminal of the battery is the shorter line. In this circuit, there are two switches, S1 and S2. So this is an example of RL circuit, where a resistor and an inductor is connected in series across a battery. Let's analyze the circuit. Let's first close switch S1. Then what happens is you have electric current going in the direction shown by the arrows, like that. Let's represent the electric current by the letter I. As you will see in a minute, I is not a constant. Its value will increase in time. Now we shall demonstrate this very fact. Let's analyze this circuit using Kirchhoff's loop rule. Let's take the loop to go like that. We note as you travel through the battery, you're going from the negative to the positive terminal, so the term will be plus E. Now through the resistor, you are traveling in the same direction as the direction of the electric current. So the voltage term for the resistor will pick up a negative term, minus IR. What about the inductor? Note that the current goes from this point to that point when you travel across the inductor. So this point, let's call it A, must have a higher potential than that point, let's call it B. As you travel through the inductor, the potential difference term for the inductor will pick up a negative term because you're moving from a point with higher potential to a point with a lower potential. And that potential term is quite simply L di dt, as we have seen in the previous video. There aren't any other components left in this loop, so all these terms added together must give you 0. Essentially, this is a differential equation in I. Let's rearrange the terms a little bit. When you do that, you get E minus IR over L equals di dt, which can be further rewritten in the following manner: minus R di over E minus IR equals minus R over L dt. Now we can integrate this equation like that. Upon integrating, you will see that the solution for the electric current as a function of time is as follows: EMF over resistance times 1 minus E to the power minus R over L t. This solution shows the electric current in this RL circuit actually increases with respect to time, and the growth is exponential. We note that when the switch S1 is closed, at that moment, namely at t equals to 0 seconds, the current is 0. After the switch is closed for a very long time, namely when t tends to infinity, or at very large time, this term will go to 0, and the electric current in the circuit will tend to stabilize to the following value, namely EMF over the value of the resistance. Let's try to graph the behavior. So if you plot I versus time, you're going to get a graph that goes like that, namely an exponential growth, with the asymptotic value, or the maximum value here, is EMF over the resistance. How fast the electric current gets to the maximum value depends on that term. As you can see, that term consists of an important ratio, namely L over R. This ratio is called the time constant of that circuit, which is usually denoted with the letter tau. So the interpretation is, when the time constant is small, the electric current in the circuit will get to the maximum value very quickly. When the tau or the time constant is larger, that process takes more time. Next, let's work out the rate of change of that electric current. From this expression, it is just a matter of taking the derivative of I with respect to t. When you do that, you get E over L E minus R over L t. We can immediately see that as t tends to infinity, namely at very long time, after that switch S1 is closed, your di dt tends to 0. What that means is the rate of change of current tends to 0. The interpretation is the current tends to stabilize. That's the reason why you have the rate of change of current goes to 0 at very large time. So the picture is, after a very long time, the current in the circuit will simply becomes E over R. Now let's see what happens at that instant. We open switch S1 and we close S2. Now what will happen to the current in that circuit? That means in this equation, we will cancel out the E term. There is no more battery involved as far as this circuit is concerned. So let's try to solve this equation. This is again a differential equation. Let's rewrite the terms. The right hand side is L di dt. Rearranging the terms, you have minus R over L dt equals di over I. So when you integrate that equation, you get minus R over L t equals natural log of I, which then can be shown to assume the following form, namely current at any time t equals E over R E minus R over L t. What that expression is showing, at t equals to 0, the current was maximum, namely it is the EMF over resistance, as shown here. And as time progresses, the current starts to decay, and after a very long time, the current tends to 0. So that's what we mean by the current decay. Let's try to plot this on graph, I versus t graph. So you have a decay, it goes like that. So it starts from a maximum value of E over R, namely that, and goes all the way to 0 at t tends to infinity. How quickly the current decays in a circuit is dependent on, again, the time constant, namely L over R. So let's assume you have two graphs. One graph is like that, and the other graph is like that. So the time constant for the red graph is smaller than the time constant for the blue graph. Now let's look at a problem. Problem 1. In an RL circuit, the battery EMF is 6 volt. The circuit resistance is 170 ohms. The current in the circuit takes 60 microseconds to go from 0 to 5 milliampere. Find the final current in the circuit, what is the inductance of the inductor used, and calculate the time constant of the circuit. So we know the current at any time t is given by the following expression. EMF over R, 1 minus E minus R over L t. So we are looking at the instant when the current in the circuit is increasing. So part A asks us to determine the final current, namely when t tends to infinity, the current goes to the value of E over R. E is 6 volts. Resistance is 170 ohms, so 6 over 170 is 0.0353 ampere. Let's look at part B. What is the inductance of that inductor used? Now we are told that when t is 60 microseconds, the current is 5 milliampere. So let's substitute that in this expression. right there. So when I is 5 milliampere, milliampere is 10 to the power minus 3. EMF is 6 volt, resistance is 170 ohms. 1 minus E to the power minus R. R is 170 ohms. L we don't know. That's the inductance that we want to determine. And the T is 60 microseconds. So micro is 10 to the power minus 6 seconds. And one can work the following out. E to the power minus 170 over L times 60 times 10 to the power minus 6 to be 0.8583. And by taking the logarithm of both sides, we can solve for the value of inductance. And when you do that, you get the following number, 0.0667 Henry. Now part C, calculate the time constant. So time constant is given by inductance over resistance. Inductance is 0.0667 from part B. Resistance is given 170 ohms, and that's going to give you an answer in seconds. When you do the calculation, you get the time constant to be 3.92 times 10 to the power minus 4 seconds, and that solves the problem. Problem 2. An inductor with inductance 4 Henry and resistor with resistance 10 ohms are connected to the terminals of the battery with an EMF of 12 volts. Assume that the battery has no internal resistance. So here we are dealing with an RL circuit. Find the initial rate of increase of current in the circuit and also rate of increase of current when the current is 1 ampere. In the discussion, we worked out di dt, the rate of change of current, to be EMF over inductance times E to the power minus R over LT. So initial rate of increase of current, that is when T is 0, then di dt is quite simply E over L. E is 12 volt and L is 4 Henry. So you get 3 ampere per second. What about the rate of increase of current when the current itself is 1 ampere? So for that, we need to know what the time is when current is 1 ampere. Remember, the expression for I as a function of time is E over R, 1 minus E to the power minus R over LT. So for part B, when I is 1 ampere, E is 12 and R is 10. 12 divided by 10 is 1.2. times 1 minus E to the power minus R. R is 10, L is 4, T. And solving for T, you get T to be 0.7167 seconds. Now all we have to do is to substitute this value of time inside that expression to get the rate of increase of current at that time. And when you do that, you get di dt equals EMF over L. So EMF is 12, L is 4, so that's 3. E minus R is 10, L is 4, so minus 10 over 4 times time, which we have just determined, 0.7167. And that's going to give you 0.5 ampere per second. And that solves the problem. Thank you for watching.